All right, this one I think is kind of a quick, fairly straightforward, easy one from the same packet that the other problems came from. This is from 2014. I think it's E3, but I forgot to write that down, so I don't know. What we have in this problem is we have a loop of length L and height L over 4, starting with an initial velocity V naught, moving to the right as it enters a magnetic field directed into the page. So the things we're given in the problem are the mass, length, resistance, initial velocity, and the presumably strength of the magnetic field. I'm not going to jump into this framework right away because the first part of this question kind of asks some purely conceptual things about the speed of the loop and how it changes or doesn't change as it moves through this region. So if you've already gotten accustomed to the idea that this magnetic induction sort of thing is equivalent to inertia, then you kind of already know the answers. You know that in either case, when this thing has the flux first begin to change as it enters this field, it's going to oppose that change and slow down. There's no inertia once the thing's moving in a constant way, once the flux is no longer changing here. But once the loop begins to exit here, that magnetic equivalent of inertia kicks in again, and this thing will oppose leaving and slow down yet again. For now, that's the only detail I'm going to really give about it, because the last part of the question asks about acceleration direction, so I figured that's the time to really look at the nitty-gritty of the directions and so on. Although I will point out one aspect of this that kind of ties to something we discussed in a previous Q&A session was that this is sort of like the magnetic braking example that I gave you guys, where there was a metal spatula swinging down into a magnetic field, and that metal spatula slowed down dramatically, not as much when it was slotted, and not as much when it was turned into a fork. Same thing is happening here. As this chunk of metal enters the field, it experiences a strong force to the left. Since the next part of the problem is asking about current, we'll go ahead and apply this machinery. So, magnetic field is given, so that's easy. Once again, we've got a situation where the flux is pretty straightforward to calculate because the magnetic field has constant magnitude and the loop's area and angle doesn't change. However, the amount of loop that's inside the field does change. So I drew this phantom loop up here to show as it enters the field, you could call the segment that's inside the field already x, and the rate of change of x initially is v naught. In the usual way, we divide the induced EMF by the resistance, and we get the final expression. As for the direction of the current, well, again, there's two different ways of looking at it. One is the Brian-Offit right-hand rule, where you notice that as this loop begins to enter the field, it sees more and more and more magnetic field lines that point into the page. And so to oppose that change, to oppose the into the page field, you want to have field lines that point out. and that gives you a counterclockwise current. It didn't ask for this, but if you apply a similar logic to when the loop begins to leave the field, you could say, well, now having gotten accustomed to seeing a nice strong magnetic field and constant flux inside of it, you're now taking that flux away. And this means that the loop will once again seek to counteract this change. This time, the change that is counteracting is a decrease in field, so it wants to increase the number of field lines into the page, and so you get a clockwise current. If you wanted to look instead at what's happening to the front edge of the loop as it enters the field, then you could do the usual thing where you imagine the positive charges inside the bar moving to the right inside of a field that points down, and so they experience a force upwards, and that gives you your counterclockwise current to begin with. As the loop leaves the other side of the field, the back edge that's still inside has positive charges moving to the right inside a field that points down, so you have a current up through the back edge of the wire as the loop leaves, and that gives you the clockwise current. While we're at it, let's use that front edge and back edge argument to explain why there's nothing going on while the field is completely immersing the loop. If you've got the bar moving to the right inside this field, then you get an upward force on the pluses on this side. But since this thing has now become immersed, you also have an upward force on the protons on that edge. So all that really happens is that the top of the loop starts to get a positive charge, and the bottom of the loop starts to get a negative charge, and you could think of that as kind of being analogous to a Hall voltage. The next part of the problem asks you to set up, but not to solve, a differential equation for the velocity of the bar, I believe as it enters the field.
So we can once again use F equals ma.
Since it says don't solve, then we can stop there. But you can see that this ends up being not that difficult an expression to solve for. You get, once again, an exponential decay as it enters, and you would get another exponential decay as it left. Also, I kind of like that you finally see why they bothered giving you the mass of the loop, because that wasn't needed up till this point. As for the acceleration upon leaving, well, we've kind of already done all the heavy work over here, but to reiterate, the part of the loop that still remains inside the magnetic field is seeing a smaller and smaller flux, and so it seeks to oppose that change in flux by producing more and more field lines into the page. And so you can use your favorite method to reassure yourself that it is in fact a clockwise current.
If the current is clockwise, then that means that it points up.
And the tailing edge of the bar, a current up and a magnetic field in gives you a force to the left.